Hello and welcome to our lesson on polar coordinates and equations. So this is going to be a pretty surface level introduction to polar coordinates, polar equations, basically the polar coordinate system, so that when you're getting to, say, AP Calc 1, you're not seeing these things for the first time. But some of it, I'm not going to lie, can get a little complicated. I just want to introduce you to the topics so that you have a bit of a foundation before you get to the next level. So the polar coordinate system, before we start with that, the system that we've been using to graph functions up to this point, we call that the Cartesian coordinate system. So a Cartesian coordinate system is a system where you have functions in terms of x and y, you have points, which we call rectangular coordinates that are in terms of x and y. The polar coordinate system is what we're going to be looking at today. Basically provides us another platform for functions that have symmetries that are just a little awkward to express in terms of x and y because they're relationships between angles and radii, things that we deal with in trig. Okay, and so there are some commonalities. However, both of the systems serve as a way of locating points in a plane. So both Cartesian and polar coordinate systems are that. They are locating points in a plane. Both of them are centered at the origin. It's just the origin is called a couple different things in the polar system. So in the polar system, sometimes the origin is called the pole, and sometimes it's lettered with the label, or labeled with the letter O. And in the Cartesian coordinate system, the origin is at the point 0, 0. It's slightly different for the polar, but I'll get to that in a second. Now, in place of the positive x-axis on the Cartesian system, we have what we call the polar axis on the polar system. And if you take any point P in the plane of a polar system, you can create a segment between that point and the origin. And so the segment, which we'll call OP, from the origin, from the pole to that point, has a unique positive length, and we're going to call that length r, as in radius. And then finally, we're going to let theta represent the angle that's measured counterclockwise between our polar axis and that segment. And so the coordinates of our point P are going to be represented by the radius, length, and the angle that it creates. Okay, now again, the origin, it's 0, 0 in our Cartesian coordinate plane, but in the polar system, it's if the radius is 0, so it's sort of a unique point. The radius is 0. There is really no angle. It's irrelevant when the radius is 0. So instead of calling the coordinate at the origin 0, 0, we're going to call it 0 theta. Theta really, it can be any angle. If the radius is 0, you're stuck there at the origin. Okay? So let me try to paint the picture for you a little bit better here now that we've got the words out of the way. So in the polar coordinate system, we are looking at a polar axis instead of the positive x-axis. So that's just changing of verbiage, whatever. And then you have some point out here in your grid, and between the origin, that's this point here, and that point, you can create this segment, and it's going to have a unique length, which we will call r. So this is going to be r here. And then the angle that's created between that radius and the polar axis, we're going to call theta. And so the point, the coordinate in the polar system here for that point is given by the radius length and the angle measure. Alright, so now what we do is we transfer this to a bigger picture, just like when we graph on the Cartesian coordinate plane. So let me take you to Desmos for a second here because it does a good job. So this is like a typical, negative 10 to 10 axis where we would graph rectangular coordinates on the Cartesian plane. This is what it looks like in the polar system. So you have a radius length that's going to go out there, and you have these angle measures as well. So it's, instead of x's and y's, they're radius lengths and angle measures. Okay, so Desmos actually does both, which is kind of nice. But let's practice, just so we get a feel for this, plotting a couple of polar coordinates in this polar coordinate system. Plenty of practice doing the other stuff. So first it says, let's plot the point 4 and then 5 pi over 6. So 4 represents a radius length. 5 pi over 6 is our angle. So I would locate the angle. The angle 5 pi over 6 is here. But we start at the origin, and if we want a radius of 4, each one of these markers, you can see here, each one of these markers is 1 unit in length for the radius. So that's a radius of 1, radius of 2, radius of 3, radius of 4, in both directions there. It's a positive radius length in both directions. And we can keep going, but we found our angle, right? Our angle of 5 pi over 6 is here. We just want to go out to a radius of 4. So 1, 2, 3, and 4. That would put point A right there. So that is where the point 4 and 5 pi over 6 is located. Okay, so now let's try the next one, which I intended to be 4 pi over 3. So let's just pretend that's what I had there. Okay, 4 pi over 3. 4 pi over 3 is this angle right here, but we only want a radius length of 3. So I'm going to go 1, 2, and 3, and that is where B is located. That's an angle of 4 pi over 3 and a radius length of 3. And then C is at pi over 3 with a radius length of 7. So pi over 3 is this angle here, but we want to have a radius length of 7. So 1, 2, 3, 4, 5, 6, 7 puts point C right there. And then the last one is a negative angle, which just like when we were using the unit circle is directional. So instead of going up pi over 3 radians to that angle, we're going to go down. So if positive pi over 3 is here, then negative pi over 3 is going to be here. It's the same distance in the opposite direction. So that's actually 5 pi over 3. Negative pi over 3, same thing. Those are coterminal angles. So then our angle, let me pick another color here. This is our angle, right, that we're looking at, but we only want a radius of 1. So I want to go there, which means point D is right at that spot right there. Okay, so not too bad, just plotting points. It takes practice. It's definitely a different way of thinking. But because we have points now in two different systems, it's going to be helpful for us to be able to go back and forth. So we need to be able to take a rectangular coordinate and convert it to a polar coordinate or vice versa. So we got to be able to convert back and forth now that we have two systems. And so to see how the conversions work or the connections, what I'm going to do in this picture is just merge the two systems. So let's pretend that this is our positive x-axis and our polar axis at the same time. So that this point P is, let me use black here, this point P is representing a polar coordinate and a rectangular coordinate at the same time. Okay, so this would be our radius length. This would be the angle that's created between that radius and the polar axis. Now the rectangular coordinate has some distance that it's traveled up along the y-axis, and it has some distance that it's traveled over along the x-axis. So that x value and y value come from those two distances. Okay, so we have some radius length created from the origin to the point. We have an angle created from the radius to the positive x-axis or the polar axis. And then we've gone out or over a certain distance and up a certain distance to create that rectangular point. Okay, so that's merging the two. Now, how do we get from the one to the other? How we tie this all together is using some things we've learned in trig. So one of the things is using the side lengths. Well, this is a right triangle here. And we know that in a right triangle, that x squared plus y squared, in this case, has to equal r squared. That's our Pythagorean theorem, right? A squared and b squared equals c squared. So r squared equals x squared plus y squared, or we could say r is the square root of x squared plus y squared. So there's one takeaway. Another, we know how to write ratios using sine, cosine, and tangent. So in this particular case, we could say that the cosine of our angle theta is equal to the adjacent side over the hypotenuse. And so if we wanted to solve for x, in the same way the last one we solved for r, if we want to be able to solve for x in this one, we would multiply both sides by r. So we could say x is r times the cosine of theta. So now we know exactly how to get a value for r. We know exactly how to get a value for x. How about a value for y? Well, I could say that the sine of my angle theta is equal to a ratio of the opposite side over the hypotenuse. And again, if I wanted to solve for y, just multiply over r. So then y is going to have to equal r times the sine of theta. And then one last relationship. Let's use our last trig function. Let's use tangent. Right? If I wanted to write a ratio for the tangent of theta, then it's going to be equal to the opposite over the adjacent side, so that would be y over x, and we could actually then use this to solve for theta. That means that theta is going to be the inverse tangent of y over x. So if we are able to solve for r and for theta and for x and for y, then we should be able to convert between polar and Cartesian coordinates, right? So all that information is right here in these boxes. So let's try this out. For this first one, we have a polar coordinate. I know it's polar coordinate because this is an angle here, so this has got to be a radius. So let's start by finding x, and then we'll find y so that we can convert. So x, as we just saw, is the radius times the cosine of our angle. And that is an angle that we can find in the unit circle. So negative pi over 3, let's figure out the cosine for that negative pi over 3. Happen to have a unit circle handy. So pi over 3, that's here, which means negative, let me get my highlighter. Pi over 3 is here, which means negative pi over 3 is here. We just looked at that a minute ago. So this is negative pi over 3. We want the cosine, which is a half. So this is really 2 times a half, and 2 times a half is 1. And to get our value for y, it's 2 times the sine of negative pi over 3. So again, back to the unit circle, the sine for negative 2 pi over 3, that's negative radical 3 over 2. So this is really 2 times a negative radical 3 over 2. So those 2's will cancel and give us a negative radical 3. So that means the polar coordinate 2 and negative pi over 3 is equivalent to the rectangular coordinate with an x value of 1 and a y value of negative radical 3. Whew. Okay, so there's one. Let's try it again. This one I think is a little easier. Again, I know this is a polar coordinate because this is an angle here, so this is going to be a radius. So x is the radius times the cosine of our angle. Pi over 4, I know that one, but let me just show you. So pi over 4 is here. That is a sine and cosine of radical 2 over 2. That's kind of nice. So radical 2 over 2 for both. So here, cosine of pi over 4 is radical 2 over 2. So this is negative 3 times radical 2 over 2, which makes it negative 3 radical 2 over 2. And then the same thing is going to happen here because the sine of pi over 4 is, again, the same value. So negative 3 times radical 2 over 2 is still negative 3 radical 2 over 2. So this polar coordinate of negative 3 and pi over 4 is equivalent to a rectangular coordinate at negative 3 radical 2 over 2 and negative 3 radical 2 over 2. Alright, so I think going that direction is pretty straightforward. It's the other direction that can be a little confusing sometimes. Not at all times, but this one, the first one, is actually, it's not so bad. So this is a rectangular coordinate. Neither one of these are angles. This is an x value and a y value. So I need to find r, and I need to find theta. Well, we know that r squared is equal to x squared and y squared. So radical 3 squared is 3, negative 1 squared is 1. That means r squared is equal to 4, so our radius has to be 2. So that wasn't bad. And the other thing we know is that the tangent, let me go green here, the tangent of our angle has to equal a ratio of y over x. So in this case it's negative 1 over radical 3. So we're looking for our angle to be the inverse tangent of negative 1 over radical 3. Now, normally I would say just go ahead and get the decimal for that, but this is, again, something we should recognize from the unit circle. So negative 1 over radical 3, that we can achieve when we divide a y value of 1/2 by an x value of radical 3 over 2. If one of these is negative, right, then that y divided by that x is going to create that fraction that we have here. So what we need to establish is where is this? So we need coordinates like this, right? We need we need a radical 3 over 2, and we need a 1/2, and we need one of them to be negative. The question is which one? So we go back to our original coordinate here, and we decide, well, what quadrant is that on the Cartesian coordinate plane? Well, a positive x and a negative y. Think about this, positive x, negative y, that's going to happen in quadrant 4. And so if this is in quadrant 4, then our angle has to be in quadrant 4. So let me go to my unit circle. I'm looking for, remember, a radical 3 over 2 for the x and a 1 over 2 for the y. And that is going to happen right here, where that's negative. And so that's 11 pi over 6, or more concisely, we can say negative pi over 6, right? This is positive pi over 6. This is negative pi over 6. So I'm going to go negative pi over 6 for that angle. And it wouldn't be wrong to say 11 pi over 6. It's just, again, a little more concise to say that smaller angle. So we're going to go with our angle. Let me erase all this, so sorry. Our angle is negative pi over 6. So we have our, what happened to my theta? It looked so bad. We have our radius, we have our angle, which means these coordinates are 2 and negative pi over 6. Okay, so 2 and negative pi over 6 are the polar coordinates equivalent to the rectangular coordinates radical 3 and negative 1. Now that one, which actually got a little tricky with the angle there, was the easier of the two. So I'm going to show you another one. I don't want you to freak out about this. Just if you have a little bit of understanding, I'm happy. Again, this is supposed to be scratching the surface here. So as long as you get the intro, you should be fine moving on to the next level. Again, this is a rectangular coordinate with an x value of 2, or x value of negative 3, y value of 2. Let's find the radius first, because that's easy. So r squared is going to equal negative 3 squared and 2 squared. So that's going to be 9 and 4, which is 13. So if r squared is 13, r is going to be an exact radical 13, some decimal, not worried about the decimal. Okay? The other part here is that the tangent of our angle is equal to a fraction of the y value over the x value. Now we're not going to get negative 2/3 from the unit circle, and so we're going to use our inverse tangent. So theta is going to be equal to the inverse tangent of negative 2/3. And here's where this gets tricky. Okay, this gets dicey. So what quadrant is this in here? Negative x and a positive y is quadrant 2. So this angle has to be in quadrant 2. This is quadrant 2. So we need to be in quadrant 2 when we find our new angle. However, when we use our calculator to find the inverse tangent of negative 2/3, we get negative 0.59. Now that's hard to conceptualize. That's a value that's in radians, and we don't think in radians, so I just want to convert that to degrees for you. Negative 0.59-ish times pi over 180, that's how we convert to, sorry, what am I doing here? 180 over pi, that's to convert to degrees, divided by pi. It's a negative 34-ish degrees, okay? So think about what's happening here. We asked it to calculate an angle for us, and we're looking for an angle that's supposed to be over here in quadrant 2, but it gave us an angle in quadrant 4. That's where negative 33.8 degrees is, okay? So we don't need the angle that's in quadrant 2. We need the same angle, but we need it to, or the angle that's in quadrant 4. We need the same angle, but we need it to be in quadrant 2. So we need the angle, the same reference angle, just in another quadrant, which is 180 degrees away, or pi radians away. So it takes us recognizing that we're in the wrong quadrant here, and we just don't tend to think in radians. So I don't know if you calculated that, if you were going to be like, oh, this doesn't feel right. So again, it's a weird thing. So don't, if you see it, if you understand what I'm saying to you now, then that's good. If you wouldn't have seen that on your own, don't feel bad. I don't know that I would have either. It took me a little bit of thinking to figure that out. So this gives me a value of this is about negative 0.59, but that is in quadrant 4. That's in quadrant 4. So we have to add pi radians to get to quadrant 2. So a negative 0.59 plus pi radians is going to be about negative 0.59, oh my gosh, fat fingers, times pi radians is about, oh, not times, plus, what am I doing? Plus pi radians is about 2.55. So 2.55 radians. So our angle, which I know I tried to tell you this was a bad one. Our radius was radical 13, and our angle is about 2.55 radians. Definitely worse. Sorry. Okay? Just an intro. If I put this on your practice, it will not be one of those number 4 type of problems. It will be one like this that works out. Okay, I just want you to see it, that they're not always so straightforward. Okay, so now that we have a little bit of a grasp on the coordinates and going back and forth from Cartesian to polar, what I want to show you now is, again, just a brief intro into polar equations. So just like Cartesian, or what we call rectangular equations that are in terms of x and y, a polar equation will have to be in terms of r and theta. Okay, and a solution for an equation in terms of x and y will have an x and y. This is going to have an r and a theta. And when we're rewriting, again, we got to be able to go from one form to another. We're basically going to use the same two facts that we just used in converting. If I want to go from a rectangular form to a polar form, I know that x has to equal r cosine theta, so I can replace every x with r cosine theta, and I know that y is r sine of theta, so I can replace every y with r sine of theta and then just simplify. So for example, if I wanted to rewrite this rectangular form into polar form, x is going to get replaced, that is r times the cosine of theta squared instead of x squared, minus 2 times instead of x, r cosine theta, plus instead of y, it's r sine of theta squared, equal to 0. And then just some simplifying from here. So I'm going to square and square. This is r squared that r looks so weird. Sorry. R squared cosine squared theta minus, we can multiply here, 2r cosine theta plus square here, r squared and sine squared theta. Now, when I see a cosine squared and a sine squared, hopefully you're seeing this too, we can use a Pythagorean identity. So if I move those two terms together, r squared cosine squared theta and r squared sine squared theta, I'm just rearranging right here, then I can actually factor out an r squared from those. So if I factor out r squared, it leaves me cosine squared and sine squared, which is nice because sine squared and cosine squared together makes 1, so it makes that go away. And so r squared times this is our Pythagorean identity, which is just equal to 1. Let me change colors. Equals 1. So 1 times r squared means we really just have an r squared minus 2 times r times the cosine of theta equal to 0. And I think that would be sufficient there. It wouldn't be wrong to leave it in this form here, but if you can simplify, again, when you're seeing sine squared and cosine squared, you want to try to do that. And if we could get it in terms of one trig function, that would be ideal. Okay, so r squared minus 2r cosine theta, that is the polar form of that rectangular form. Those are the same equation in two different forms, just like mind-blowing to wrap your head around that. All right, now we're going to try to do one in reverse. In reverse, this can be a much more complicated process, but again, we're trying to scratch the surface here. So what we want to try to do here is rewrite it until we get something we recognize. Let me tell you what I mean, or show you what I mean here. So 2r equal to secant of theta. So remember, Secant is the reciprocal of cosine, so I could call this 1 over the cosine of theta. And then if I wanted to, I could multiply both sides by cosine to get rid of that fraction. So I could say 2r times the cosine of theta is equal to 1. And then I could get rid of the 2 that's on this side by dividing it over. So I could say r times the cosine of theta is equal to a half. And the reason I would want to do that is because I know what r cosine theta is. We defined that r cosine theta is exactly x. So instead of replacing x with r cosine theta, I can now replace r cosine theta with x. So x equals 1/2 is our equation. So it's basically just a vertical line. Okay, vertical line on the Cartesian coordinate plane, which is bananas. And that process can be so ugly. Okay, but that's generally the idea. All right, so lastly, I want to show you how to graph a couple of very basic polar equations. So when we're graphing, remember when we start graphing, like in basic algebra classes, if you're going to graph y equals x squared and you had no idea what it looked like, you would make a table of values where you pick some values for x and you plug them in and get your value for y, and then you have points that you can plot. We're going to go about the same process here. It's just r's and thetas. Okay? So the first one, r equals 3, it's a lot like just graphing a y equals 3 or just graphing an x equals 3. We only have one variable, which means the other doesn't matter. So if I was going to make a table here, I have r, I have theta. So if r equals 3, that means r equals 3 no matter what theta is going to equal. So I can call my angle 0, I can call it pi over 2, I can call it 3 pi over 2, I can call it whatever I want. The radius has to be 3. So what is that going to look like when we connect all those points? So my axis, let's be careful with the axis here. This is a radius of 1, 2, then 3, and again radius of 1, and then 2, and then 3. It's going by 2's here. So a radius of 3, let me make sure I'm color-coded. So if I had an angle of 0 and a radius of 3, an angle of pi over 6 and a radius of 3, an angle of pi over 2 and a radius of 3, what's going to happen if we have a radius of 3 no matter what? Is we are going to be looking at the equation for a circle. So I'm just going to do a couple more so I can follow along with my points. No matter what, if the radius is 3, then when I connect these points, oh my gosh, so bad. Okay, I'm going to try. Oh no, I can't do it. It's charted at one fluid motion, but I'm going to try my best here. Okay, luckily I have a cheat tool to fix that for me. Okay, so you get the idea. Let's look at the next one. So the next one is the reverse effect. So I would still go about this by trying to turn that off, make a table. And so r and theta, this time it's theta is always 2 pi over 3. So theta is going to be 2 pi over 3 no matter what r is going to equal. So I could have a radius of 1 or a radius of 2 or a radius of 3. My angle is not going to change. So how will that look? Well, if my angle doesn't change, if I'm at 2 pi over 3 with the radius of 1, or 2 pi over 3 with a radius of 2, or 2 pi over 3 with a radius of 3, if my radius isn't changing, then that ends up being a straight line here. A straight line through that angle, 2 pi over 3, which is, oh, yeah, well, yeah, you get the idea. Okay, so there's that guy. Now, the third one, again, is a pretty basic example, but this time we have r and theta. So it works just like any other function, okay? We're going to pick some values, and we're going to plug in and see what happens. Now, what's going to be easier to choose for, based on the way this is set up? Sorry, that was just so sloppy. R, theta, and I think based off the way this is set up, it's going to be easier for us to input values for theta and figure out what our radius is going to be. So picking some values for theta, like, let's say theta, our angle is 0. Angle of 0, if I put a 0 here, okay, then 2 times the cosine of 0 is what I'm looking for. 2 times the cosine of 0, sorry. Cosine of 0, remember, cosine of 0, 0 is right here, cosine is 1. So that's going to be 1 times 2, which is going to be 2. And let's go to an angle of, how about pi over 6? Okay, pi over 6, 2 times the cosine of pi over 6 when I plug that in. Cosine of pi over 6 right there is radical 3 over 2. And if I multiply 2 times radical 3 over 2, then I'm just left with radical 3. So I get a radical 3 for my radius, and that is about 1.7. Let's jump over to pi over 4. Okay, pi over 4, what's that going to look like? Well, the cosine of pi over 4 is radical 2 over 2. So it's going to be 2 times the cosine of pi over 4 when I plug it in. That's 2 times radical 2 over 2, which is just radical 2. So I get a radical 2. And that's going to be about 1.4. And then let's jump to pi over 2. And I don't know how many of these you want to do, but I think you'll kind of get the idea of what's going to happen here. At pi over 2, so 2 times cosine of pi over 2 at, sorry, wrong thing. Pi over 2, our cosine is 0. So that's 2 times 0, which is just going to be 0. And let's start to make the picture and see what's happening here. Okay? So a radius, or an angle of 0 and a radius of 2. Angle of 0, radius of 2, that's going to be right here. And then an angle of pi over 6 and a radius, that's about 1.7-ish. It's going to be like around here. And then a radius of pi over 4, an angle of pi over 4 and a radius of 1.4 is going to be a little lower than that. So I'm on this angle right here. That's going to be 1, and 1.4 is going to be somewhere around there. So this is going to be like, lost it, like about here-ish. And then at pi over 2, we're down to 0. Well, that's not 0. Cosine of pi over 2. What am I missing? Cosine of pi... Why does that feel wrong? Feels like that should be a 1. I'm having a moment. Don't mind me while I have my moment. Oh yeah, I skipped pi over 3, that's why. So this is actually right. I'm sorry. I just went from this, I had a moment in my head. I went from pi over 4 to pi over 2 and I skipped pi over 3. I'm like, I'm missing something here. Let me go ahead and put pi over 3 in my table. Pi over 3. It's like, what am I doing? Cosine, if I plug that in, I'm running out of space, so I'm plugging it over here. If I did 2 times the cosine of pi over 3. Well, at pi over 3, our cosine is a half. So that's not too bad to graph. Let me go back here. So this is 2 times a half, which is going to be 1. So at pi over 3, we're at 1. That's a nice point. Why would I skip that one? I don't know. So at pi over 3, we're going to be at 1. And then at pi over 2, we're down to 0. And then what's going to happen if I started to plug in the other angles like 5 pi over 3 and 11 pi over 6, is we're going to end up with the same values, but they're going to be negative. So at 5 pi over 3, I'm going to be at a negative 1, and then here I'm going to be at a negative 1.4-ish, and then I end up over here at negative 1.7-ish, and my drawing is probably not doing this justice, but these points are going to connect to make a circle. And there it is. Okay? So that was definitely a lot more work than the other two. It's kind of nice when a variable is missing, but that's true for any function. If I'm just graphing a y equals, I get a horizontal line. If I'm just graphing an x equals, I get a vertical line. So if I'm missing a variable, radius or a theta, then it's simple to graph. Otherwise, it takes a little bit of work until you get more familiar with how these functions are supposed to appear, just like we know so much about our other polynomials, right? If I know if I'm looking at an x squared, how that's supposed to look, or my rationals, I know 1 over x. I know my parent functions in the Cartesian coordinate plane very well. Eventually, maybe you get as comfortable with these. I'm not, but hopefully this surface level introduction is good enough to get you started. All right, so give it a shot. Try out the practice problems, and as always, if you need some extra help, then just reach out. Till next time, take care.